Yep. Okay. I hope you hear me well. I try not to move too much to not disturb the system. So today I'm going to give you a reinforcement learning tutorial number 1, which will be covering the Markov decision processes, dynamic programming, probably Monte Carlo methods if we have time, because we have just 45 minutes. Now please go to Collab. Repository is tutorials, so tutorials week 2, and go to reinforcement learning MDP _ MC task or solutions. So firstly, I have already run these cells, and you don't need to run this one because it's not working, but it's fine. Okay, so firstly, before starting reinforcement learning tutorial, before doing MDP, I would like to give you a very small, brief 2-minute introduction to OpenAI Gym. I don't know, I think many of you are familiar, but for those who don't, OpenAI Gym is a developing toolkit for reinforcement learning. It allows to use many different environments for reinforcement learning tasks and not bother about like coding your own game, your own environment, like, you know, throwing actions and thinking about how can you program them. OpenAI Gym basically allows us with several lines of code implement our own reinforcement learning algorithms and not worry about like anything. It just treat it like a black box. So I will sit for this and for next. Okay, so this is a small like introduction on how can you run OpenAI Gym. So first of all, we would like to, of course, import OpenAI Gym. It's already pre-installed in Collab, and you want to call the make method, and as an argument, you will put the name of the environment that you are going to use. So here it's cartpole. Unfortunately, in Collab we won't see it. I didn't figure out how, it didn't work, my plan. But if you clone the repository, if you do it locally, like it will work and you will see the pop-up window of, I will tell it in a second. So firstly, you receive an object of an environment. This environment, before you run it, it should be, of course, reset. And very important. And what's important is that reset not only resets our environment, resets the agent state, the rewards, etc., etc. It also returns the initial state, which can be useful if you're going to do some iterative reinforcement learning algorithms. So, and the main part is if we run in Collab, nothing will happen, or error will, okay, it doesn't matter. So if we run it in, so basically this is a loop which runs our environment for 100 time steps. In this loop, we're going to render our environment. It will work in local Jupyter notebook, which will allow us to display the environment on your notebook. And the most important part is this step function. So basically, this is exactly what I meant when I said black box, because it allows us to pass some action to an agent in the environment and allows us to receive some state which our agent got into when he made this particular action. The reward he got, some flag, which done flag, which is basically if our agent has died or if it has I don't know, won the game. If the game has been terminated in one of the states, this is basically the flag that shows this to us. And if info is some, can be some useful debug information. I haven't used it ever, so I don't know, probably many of you have, if you like to get into nooks and crannies of, I don't know, OpenAI gym libraries. Yeah, but this is basically it. This is how you run a Jupyter, a OpenAI gym environment in Jupyter Notebook. Very simple. We don't even have to think about it. Yeah, so this is like a small introduction. And now, yeah, and this is like what I basically told you about the environment step. And if you want to see, and yeah, the OpenAI Gym has lots of environments in it, like Atari games, which are baselines for many reinforcement learning games. Like the simulations, for example, like Professor Weissen showed you on his lecture, like of a person flying away. Yeah, this environment can be found in OpenAI Gym. Some robotic arm simulations, some toy problems that we're going to cover today, etc., etc., etc. You can go either to the website or you can look at it through this code, but we're not going to do it right now. We are going to go straight to Markov decision processes. So I hope you, from the lecture, you got an idea what it is. But if you have forgotten, like a small recap, Markov decision process is some kind of framework that allows us to encapsulate the world using some set terms, right? So these terms, or these rules, right, are the set of states, the set of actions, the reward function, the transition probability function, and, well, yeah, the discount for future rewards. It's not exactly, yeah, but it's a parameter, but never mind. So if MDP doesn't have any of those, it's not an MDP. And another thing, very important thing, is it's that Markov decision processes should have Markov property. Shock, yeah. So what Markov property means is that the future only depends on the present moment, and does not depend on the past. Another thing that MDP has is MDP, usually when we talk about MDP, we mean some problem. It can be like going from point A to point Z, it can be like making your robots stand straight, it can be like grabbing something with a robotic arm, but the problem is there. How can you do it? And the answer to this and the solution to this problem is policy function. Policy function takes a state, and for every state that we give it, it gives us some action, which is which in perspective will maximize our expected long-term rewards. Yeah, and basically that's it about MDP. And another thing, yeah, I hope today we will cover two types of reinforcement learning models, problems, one of which is model-based reinforcement learning. This is exactly what we are going to do right now. It's when we know, it's like a very classical MDP. We know the transition probability function, we know the reward function, we know that the optimal policy can be found, and the model-free reinforcement learning, which is much more close to the real world. We don't really know the transition probability function, we don't really know the reward function. Yeah, I hope we will cover it also today. So let's get to the point. In advance, I say sorry for the pictures because they can be like all over the place. I will fix it, don't worry. Frozen lake, simply put, is just a grid world. And what does it mean and what are the rules? So basically we have some starting point S and we need to get to some point to the goal G, right? And this environment is 4x4, so 16 states. And when we go to this point G, we have to avoid the holes, which are denoted as H. And if we fall into these holes, we will die. We get the reward -1. Also, speaking of rewards, if we get to the G tile, we get +1 reward. For each step, we get 0 reward. And so this is what we need to do. We need to find some, the set of actions is, where it is? Yeah, the set of actions is going left, down, right, up. And we need to find some policy that will tell us what action should we take in each of these states. So, yeah, exactly what I said. And yeah, this is some poetic explanation by OpenAI. So if you want to read it, read it. My friends told me not to explain everything like OpenAI explains it. So let's do the same thing we have done with OpenAI Gym. Let's make our environment. By the way, if you're running, or I don't know, well, yeah, leave it like that. If there will be any problems with local runs of the environment, just tell me, because probably I have an older version of Gym, and this is not needed, but it's fine. Okay, so yeah, we run an environment, we render it, very pretty. We are in the starting state S. The states are encoded as a matrix, and the actions are encoded this way. So left is 0, down is 1, and yeah, so the number of states, I haven't lied to you, the number of states is 16, the number of actions is 4. So let's try to do something about it. Let's try to find some policy on a deterministic frozen lake example. So again, deterministic means that our probabilities function, as we can see here, our actions do exactly what we want them to do. So how can you read this tuple? So basically, this is the transition probability function of our environment. So basically, it means that if we do the left action in state 0, we, with probability 1, will stay in this 0 state. We will get reward 0, and we won't die. So this is false. So let's try, like, when you want to try something, first let's try something random. Let's try something, some random policy. Yeah, so this is some wrapper function that basically does exactly what I showed you in OpenAI Gym. This function receives some policy, and according to this policy, it samples some actions, and yeah, it samples some actions, it feeds it into environment step function, and yeah, and because it's the frozen lake environment, we are going to if we hit the right state, we're going to say that, yeah, if we die, we are going to like do this loop, which will break we will do this if, you understand, if we are going to do this if condition, and if we are getting there, we're going to break this loop and finish our training or gaming episode in our case. So the random policy is exactly what it means. We are getting some environment, some action space from our environment, and we just gonna sample it randomly. So you can see that our agent tried to do something, but it failed, which was expected. So let's try to do something smarter than that, right? Let's try to find some policy that will solve this problem. Let's do some artificial intelligence here. And from yesterday, I think, oh, sorry if it's too loud, I'm just, okay. From yesterday, I hope, again, sorry for the picture, I hope you remember the policy evaluation algorithm. If you don't, small recap, we have some policy, right? But we also, from the Bellman equation, we remember there are some like such function which describe our environment called a value function. We will get into some intuition, like what is a value function exactly a little bit later, but all in all, a policy evaluation algorithm, basically given some policy function, we can iteratively find some value function which will be, we can iteratively find a value function that is induced by this policy. And so here is the algorithm from the lecture, and let's define some policy evaluation function, which will be doing this. I'm going to be doing this with you. I already have some basic framework of how we're going to do this. And so, yeah, let's just do it. So firstly, we are going to sample some, so yeah, again, we have some random policy, right? No, we are going to define some policy, and let's sample some actions from this policy. So for action probability, because well, in deterministic environment it's not exactly so interesting, but as we know that policy function is in stochastic case and like in general case, it will give you the probability of doing some it will, it will give you the probability of some action, right? And so and we have some policy. So the policy receives one argument, which will be S. Okay. And then let's go through our transition function, transition probability function. So let's go and get the probability, the reward. So let's get the next state. We already have the state we're currently in. Let's get the next state, and let's get the reward, the probability of us getting into state as this state, the next state. So for the first one is probability. So for prob, next state and reward and done in environment P from state action. No action. We are going to do the. We are going to do. Oh no, we don't have. Yeah, we have S, not state. we're going to implement this function. So I have VS. So VS, it's iterative algorithm. So no, it's not like that. It's iterative algorithm. No, not exactly plus. We have sum, right? And then we're going to do the action probability multiplied by probability multiplied by the reward, our reward plus, well, gamma, but in our case because it's an MDP, gamma will be 1, which is a discounting parameter. And we're going to multiply it by V. So yeah, we have defined V as the as matrix, as array. So V next to state. Okay, I hope it works. Oh, okay, that's all right. So okay, let's do some initial policy. In this case, let's do the case where each action is equiprobable. So our basically algorithm. So the policy is basically the values of each state is going to be so basically the probability of each action at each state is going to be 0.25. So this is our initial policy. Okay. So here is the value function. And remember, right, so the value function is not the exact term, it's state value function to be correct, exact. And so here, what we got. So with this initial policy, we have evaluated our state value function. And as we can see, here's the goal, here's the starting state. We can see, for example, that, of course, all of the holes and the goal will receive a 0 value because, no, okay, no question. We will receive the 0 value because if, for example, we are doing the action in, let's say, this state, and the next action is going to be go to the right, our game is going to terminate. That's why we will get the probability there, right? We will get the probability of 0, and the state is going to be terminated. So the flag is going to be done. But also what we can see is that our value function, the closer it gets to the goal, the bigger it becomes. And so intuitively, the value function is basically tells you how promising in terms of delayed long-term expected rewards, how promising in terms of these rewards our state is going to be. So of course, this state is very promising because you are one action, one step before you hit the goal. Here, it's not so big because you can go either here or you can go either here. But anyway, here, let's say in this state, right, the probability, or in this state even, the probability of you going to the hole and terminating with -1 reward is kind of big because it's like 2 actions. So this is the state value function in a nutshell and its intuition. But if you remember from the lecture, we have another very important function, which is called Q function or action value function. And this function it seems similar, yeah, from the value function, but very important intuition is if value function kind of represents each state and how promising it is in terms of rewards, this Q function represents how promising in terms of rewards will be this action performed, a particular action performed in a particular state. So as you can think, the higher the Q function is for a particular state and for in a particular state for some action, the more probably we should take it. More probably it will lead us to some good results, right? And so let's implement this formula. Let's get, so here it's going to be relatively straightforward because I already done all of this loops that I don't like to quote. So for now, so the design is so that we are going to do the Q from V, which will output for now just an array of, basically it will just, for now, just will go through the actions and not the states. And here we're going to do the, we are going to compute an actual matrix, right? For each state, we're going to compute all of the actions and all of their Q values. So for here, we're just thinking, okay, I have some state S, let's calculate how promising are the actions in this state. So it's a sum. It's a sum of probability times reward, right? Plus gamma by V in some state, in the state, in the next state, so in next state. Okay, let's try to run it. And let's see what we got. Okay, I think not bad, at least I hope so. Again, as I said, this is for each state, right? So for 16 rows and for 4 columns, we're having the some value which represents how promising is each action in each state. So now I'm going to do something forbidden, something not good, but just to illustrate my point about deterministic MDP and how easy actually it's going to solve it. And like I mean, a child can do that, right? Like why a reinforcement learning algorithm can't. So we're going to do, as I told you, the intuition, right? The higher, the bigger the Q value is, the better. So for each state, we are going to see the actions, right? And we're going to take the maximum for 4 of these actions, right? So, yeah. Let's define this greedy policy here. So it's going to be argmax, right? Argmax from Q at some state S. And this is going to be our greedy policy. We just want to see if it will work. If just starting with some equiprobable policy, computing some value function, seeing these delayed rewards is going to be enough for us to have some good policy for deterministic environment. And you're going to be shocked, guys, but we actually do have a good policy here. But again, this is a deterministic MDP. So this is not even, this is not like in MDP in some sense, because here it's more of a planning problem, right? Everything is set, nothing is going to change. Each action induces, gives us, leads us to the state we want to go, so no problems here. But what if we introduce some stochasticity into our environment, right? So in OpenAI Gym, this stochasticity is going to be introduced by the argument is slippery, and it's going to be equal to true. Boy, we have to hurry up because I don't have a lot of time. Okay, so again, the stochasticity. Let's look at the transition probability function. Here, the transition probability is that if we, in the state 0, wants to go to the left, with probability 0.333, we're going to end up in 0 state, or we're going to go down to the state number 4. So let's try to do the same thing we have been doing before. We compute the values, right? We compute the Q function. We do the greedy policy, and I can already tell you, like, believe me, sometimes it's going to win. Sometimes, of course, the probability of us winning is there, and yeah, actually we won. But we also don't think about the stochasticity. We don't take into consideration this transition probability, right? The policy that we got is not optimal in this environment for this MDP. So let's try to iteratively get even better policy. So here we are going to be doing the one algorithm, which is composed of 2 algorithms, which is called policy iteration. So policy iteration, in this not beautiful image, basically what we propose to do. As we have done it before, as we have done it now, let's have some initial policy pi. Let's try to compute some value function, evaluate some value function of this policy pi, okay? We're getting somewhere here. Then let's try to do what I've been doing. Let's try to make, let's find some, let's try to, well, we're going to be doing the Q, we're going to be computing the Q function, but you already know that from V function we can very easily in the MDP find a Q function. But yeah, getting back to the policy iteration, we want to improve our policy. How we are going to improve it? We are going to take the greedy policy from our Q function or from our V function, doesn't matter, right? And we are going to receive with that another policy which will be different from our initial policy. It's going to be a little better according to the convergence theorem. It's going to be a little better. Then we're going to take this policy, we're going to evaluate the V function, Q function, go back, greedy, and so on and so forth. And again, according to the theorems, we're going to we're going to converge in a finite number of time steps. We're going to converge to some optimal policy pi, some optimal Q function, some optimal V function. So let's try to do that very quickly, because we have 6 minutes, right? Not done. Okay, 6 minutes, it's fine. Oh, yeah, I predicted that, and I have left you the code for policy improvement. So here in policy improvement, as I said, we're going to compute some Q from our V. We're going to find again some greedily. We're going to take some best action, and we are going to create some policy which will look like I will show you. It will look, but I mean it's already we have an output. It will look like that. So if the action is a maximum in this state, we're going to put 1. This is why we're doing the I, right? We're going to do the 1. And for each action, for each state, we're going to denote as 1 the best action you can take at the state. And here is the equiprobable still stays, as you know, because the action is terminated and the value function zeroes out. So, yeah, and again, some notation. Usually, this kind of line is called policy evaluation, and this kind of line is called policy improvement. And all of this is called policy iteration. So, okay. Here, let's try to code something. So we have 2 lines of code. So yeah, we're going to do the first. We're going to get the not new policy. We're going to get some V, which will be equal to policy evaluation. Policy evaluation. Okay. Why haven't I? Okay. Our policy evaluation function. Actually, I can use like this. No. Yeah. It's going to take the environment. It's going to take our policy. It's going to take some gamma, which we have, and some theta. And next, we are going to do the new policy. New policy, which is equal to policy improvement. And policy improvement takes the environment, the V that we already computed, right? And yeah. And that's it. Now we just do it like we do it. Now we do the convergence, right? You have here 2 options. As soon as the new policy becomes equal the previous policy, you kind of stop. And but we are going to do another way. We're going to be checking the convergence. So we're going to be seeing if the V function of the new policy and the V function of the old policy will be different, if their module is going to be different by theta. Okay. Понятно. Now it's okay. Okay, now we get we have been doing some policy iteration here. It seemed it converged. It has converged. And yeah, we plot the value function. You see, it's completely different from what we have seen before. It's the paths that we can take to get to the goal are much more prominent. The value functions are bigger. They seem to be converged. Like these are the same. These states have the same values as, let's say, these states. So they are equally rewarding let's put it like that. This one is like 0.94, like what? And yeah, and here again, the holes in the goal zeroes out. Let's try it. Let's try it. Yeah, and you, like, if you have a look, oh yes, we got the frisbee. If you have a look, right, so it seems kind of counterintuitive, like it thinks that the best action if we go to the left, if in the first state, in the zero state, is that we go to the left, right, but yeah, but we need to go down, and this is all like thinking about stochasticity right here. It knows that at one point of time, the probability 0.3, it will go down. And so it thinks, okay, I will just go left and wait until I go down. So this is the policy it has learned. This is how it is. So probably, because we don't have time, as a homework, right, we don't have time. No, we don't. As a homework, I don't know if you're going to be doing this homework, I suggest you to implement the value iteration algorithm, which is extremely similar, though a little bit different from the policy iteration. And yeah, and I also have included some Monte Carlo methods for a game of blackjack. The rules, I don't know the rules, but I have put it here for you. They're still very unclear, but I hope you, but I mean, why do we need to know the rules, right? We just need to know the reinforcement learning algorithms. Yeah, and I also propose to you to try this. I haven't, like, in the task IPython notebook, I haven't, like, moved anything. I haven't deleted any pieces of code, so you can just go through it and, like, have a look what you can do with Monte Carlo algorithms for model-free environments. Okay, so that's it for me. If you have any questions, I'm going to be here waiting for you, for your questions. So thank you. Yeah, thank you so much.